Now we're going to move on to look at two variable inequalities, which in many ways behave similarly to inequalities with one variable, but with a couple important differences. The key difference is that with one variable inequalities, there were several different ways that we could express the solution, either as an inequality or on a number line or with interval notation. With a two variable inequality, the only reasonable way to express the solution is going to be with a graph. Let's look at an inequality with two variables in it and see if we can get a handle on what the solution to such a thing should look like. So here's an example, y greater than or equal to negative 2x minus 1. Notice, first of all, that equal to is part of our inequality here, which means that y equals negative 2x minus 1 should be part of whatever solution we come up with. Well, that's a pretty good starting point. Y equals negative 2x minus 1 is a linear function that we understand pretty well. Why don't we start by looking at its graph? There we go, a line with a y-intercept of negative 1 and a slope of negative 2. Now let's see if we can get a handle on the solution to the inequality. Just like with one variable inequalities, what we're looking for are values that when we plug them in to our inequality here will produce true statements. But in this case, since we have two variables, x and y, we can plug in values for both. And so our solutions are going to look like points with an x and a y value. Now, since equal to is a part of our inequality, it would make sense that points that are on the line, in other words, points that satisfy this equation, should also satisfy our inequality. Well, let's test one. Let's take this point here, that would be 1, comma, negative 3, and see if these values satisfy our inequality. So we need to plug in negative 3 for y and positive 1 for x. Evaluating the right-hand side, we get negative 2 times 1 is negative 2, and negative 2 minus 1 is negative 3. Negative 3 is greater than or equal to negative 3. That's true. So that tells us that this point is a solution to our inequality. So we know that points that are on the line are solutions to our inequality, but are there any other points out there that work? Let's test a couple points that are off the line and see what we can conclude. Let's start with this point, 1 comma negative 1. If we plug those values in for x and y, we would get negative 1 greater than or equal to negative 2 times 1 minus 1. Simplifying would give us negative 1 greater than or equal to negative 3, and that's true. So the point 1 comma negative 1 is a solution to our inequality. Now let's try another one, say this point here, that would be 1 comma negative 5. Plugging those values in, we would get negative 5 greater than or equal to negative 2 times 1 minus 1, which tells us negative 5 greater than or equal to negative 3. Now that is not true, and that means that this point is not a solution to our inequality. We could go on testing points like this all day, and what we would find is that points that are above the line in this region all will be solutions to your inequality, and points that are below the line in this region are not solutions to the inequality. And in fact, that's exactly how the solution works out. The solution to the inequality overall is the line itself, y equals negative 2x minus 1, and also all the points that are above that line. And so the way we usually describe that, or the way we usually draw it, is by shading. We would shade all the points above the line to indicate that all of these points are solutions to our inequality. Let's do another example. Now this inequality is given to us with a x and y on the same side. And so our first goal is going to be to put it into the slope-intercept form, so to speak. We want to get the y by itself. To do that, we can use our usual tools of algebra. We should probably start by moving the 3x over to the right-hand side, and we can do that by subtracting 3x from both sides. And that gives us negative 2y greater than negative 3x plus 8. Next, we need to move the negative 2 over, and we can do that by dividing. So we're going to divide everything by negative 2. And on the left-hand side, cancel off. That leaves us with y. On the right-hand side, we have positive 3 over 2x, and then 8 divided by negative 2 is minus 4. Now, we just divided by a negative number, and so the rule for inequalities does apply here. We have to flip around our symbol from greater than to less than. And so we end up with the inequality y is less than 3 over 2x minus 4. Notice in this case that equal to is not a part of our inequality. And what that means is that the line y equals 3 over 2x minus 4 is not actually going to be part of our solution, but it's still going to be important. It turns out that this line is going to be the boundary of our solution, and so we can start by graphing that. So this line has a y-intercept of negative 4 and a slope of 3 over 2. So we will go up 3 and over 2 to get a second point. Now, since this line is only the boundary of our solution, we don't want to use a solid line to complete our picture. Instead, what we can do is use a dotted line to indicate that this is only the boundary and not the solution itself. The actual solution is going to be the points that are either on one side of the line or on the other side of the line. And the way that we can determine which side is by looking at the inequality here. Y is supposed to be less than 3 over 2x minus 4. Well, when you see less than, you should think below. And in fact, that's exactly what we're going to shade. The solution will be all the points that are below the line that we just graphed. And there's our solution. Let's do one more example that looks a little bit different than the other two. In this case, we're told x is greater than or equal to negative 2. We could express the solution using just a number line, but we can also do it with a coordinate plane. To determine what the boundary is, we will once again ignore the inequality part and just look at the equals. X equals negative 2. The graph of this is a vertical line at a position of negative 2, so it looks like this. Notice that in this case, equal to is a part of our inequality, and so the line itself is going to be a part of our solution. The rest of the solution is either going to be all the points on one side of the graph or all the points on the other, and we need to determine which side it is. Well, our inequality says greater than, so your instinct should be to say above the line. The problem in this case is that a vertical line doesn't have an above or a below. It has a left or a right. But your instincts should still lead you in the right direction here. Greater than with x typically means to the right, and in fact that's exactly what's going to happen here. All the points on the right-hand side of this graph will be solutions to our inequality. Just to be sure, let's test one. If we pick our point right here, the coordinates of that would be 1, 3. And to check, we're going to take those values and plug them into the original inequality. So we plug in 1 for x, and then we would plug in a 3 any place where we saw a y, but there aren't any y's in our original inequality, so there's nowhere to plug it. The statement we end up with is 1 is greater than or equal to negative 2. That's a true statement, which means that the point we picked out here is a solution to the inequality.